Okay, chapter 7 here in 7.1. So chapter 7 is all about functions. Now I know we're all familiar with functions. We've been working with functions for a long time. So primarily we're going to be looking at functions, in this case on general sets, introducing it here. So a lot of this is going to feel like review. This first section is relatively short because a lot of this stuff is something that we're familiar with, but we have 4 things to go over. Number 1 is we're just going to review function definition. And we're going to write out our definition in terminology, some new terminology maybe for some of you, but this is going to be mostly in the language that we're used to in this course now. Second thing is looking at equality of functions. And this is going to be primarily from a set theory perspective. And then we're going to talk about functions on power sets. We're going to use a nice little example to talk about this. And then finally, we're going to go over what it means for functions to be well defined. Alright, so let's define function. So at this level, we're going to introduce some new terms for how we discuss functions. Most of them are going to be familiar. So if the relation f is a function, then it maps a set X, capital X. This is the domain, to a set Y. This is where we have some new terminology. This is called the codomain, or the image of X. So when you usually learn functions, you talk about domain and range. And as you get higher into mathematics, you realize that range and what we've been calling the range are actually 2 different things. So codomain is what we know as range. It's the set of things that your function has values of. It's all of your function values, or the set that you get mapped into. But the range is usually bigger. And we'll talk about that a little bit more in the next section as well. So your set that you map into is your codomain or your image. These are interchangeable. And this is denoted f maps x into y. So this is our kind of our set notation for functions. You may have seen this before. Some people like to use it in other classes. But you read this, the function f that maps x into y. And every element in X is related to an element in Y, and no element in X is related to more than one element in Y. So this is just kind of the set theory version of, for each input, there's one and only one output. Right? That's that's going to be what makes our functions well defined when we talk about that definition at the end of this section. So the next thing we want to talk about is equality of functions. Again, from a set theory perspective, if capital F that maps x into y and capital G that maps x into y are functions, then f equals g if and only if, remember that's my shorthand because I'm lazy, f of x equals g of x for all little x in capital X. So every single output element in the codomain has to come from the same element in the domain. And again, this is what we're used to. Two functions are equal if they equal the same thing for every value. This is just the set theory perspective. So I want to give you a couple problems to try out equality-wise in this new notation. So please determine if the following functions are equal. So I'm going to give you two pairs of functions. F of x equals x squared plus x plus 1 mod 3. G of x equals x plus 2 squared mod 3. And our x sets are going to equal 0, 1, and 2. And our y sets are once again going to be 0, 1, and 2. So pause this, try it out, see if you can figure out if these are equal or not. I am going to walk through whether they're equal or not. And the answer here is yes, they are equal. So because our domain and codomain are so small, we can do this by brute force and just actually calculate what each of these are mod 3. So f of 0 is going to be 0 plus 0 plus 1 mod 3, which is just going to be 1. G of 0 is going to be 0 plus 2 squared mod 3, and that's going to be 4 mod 3, which is 1. So those two are the same. Let's not waste space. F of 1 is going to be 1 plus 1 plus 1 mod 3, or 3 mod 3, which is 0. Let's do here. G of 1 is going to be 1 plus 2 squared mod 3, which is 3 squared mod 3, which once again is going to be 0. 9 mod 3 is still 0. F of 2 is going to be 4 plus 2 plus 1 mod 3, which is 7 mod 3, which equals 1. And G of 2 is 4 squared mod 3, which is 16 mod 3, which is going to be 1. So those are equal. So we have that x squared plus x plus 1 mod 3 equals x plus 2 squared mod 3 when x is 0, 1, and 2, and y is 0, 1, and 2. So even though these polynomials are very different, with these limited domain and codomains, when we mod 3, we have equality. So these are the kind of functions we're going to be looking at, some more unique functions. Some of them are going to be traditional, just polynomials like you're used to. Some of them aren't. So in the next example, we're going to look at a slightly more abstract case. So this would be part B. So if f maps reals to reals and g maps reals to reals, then we know that f plus g of x is f of x plus g of x. These are the old rules that you know from algebra. And g plus f of x is g of x plus f of x. So I'd like you to show algebraically that f plus g equals g plus f. So essentially we are proving the commutativity of function addition here. So pause it, try it out, see if you can get to the result. I'll start going here now. So since we're proving an identity, we're going to pick one side. I'm going to pick the left side, and we're going to work our way to the right side. So this is f of x plus g of x by our definition. Now these are just numbers, so I can rewrite this as g of x plus f of x because we're mapping reals to reals, so f of x, regardless of what x is a value, and so is g, and they're real numbers. So this is g plus f, which is nothing more than g plus f of x by our definition. So commutativity, really easy to prove. Notice we didn't actually need to know what the functions were. So this is kind of the level that we want to be thinking about is, can we prove things without relying on the function rule as much as we normally do? So we have a special function, that's the wrong color, and that is the identity function. Now we've all seen an identity function, probably more than one, before, but for any set x, the identity function maps x back onto x by, we denote it as I sub x, this is a capital X of x, equals x. And this is for all little x in capital X. Now if these are real numbers, so if x is a real number, well then I of x equals f of x equals x. That's the function we're talking about, the linear function. If x was R2, so R cross R, the set of ordered pairs, then I of x be x comma y now, would equal f of xy, which just equals xy. So you've seen identity function, the identity function before. When we apply it to specific sets, we get some well-known functions like the linear function, or just, this one's not linear. I mean, it's linear in two variables, but that's not important here. But we've seen functions that do this before. And they're called identity functions because they identify the value that you've plugged in. So that's a fun little function that you're going to play around with in the homework. Just know that this is how it's defined, and I wanted to give you these examples so you know it's not something new, you have seen it before. Okay, so our next example is how we're going to talk about power sets and functions. So we are going to define f that maps the power set of ABC into the positive integers, z plus, by capital F of x equals absolute value of x. And so we're just going to talk about this function, and we're eventually going to construct an arrow diagram. Arrow diagram. So one thing to note is our notation for functions doesn't change. So this still looks like we're plugging in one value. But in this case, x is actually a subset of the power set of A, B, and C. So that means that all x is a set. So we are going to be describing a function that maps a set onto a value, because absolute value is still absolute value. Now, what absolute value does when we're talking about sets, we're going to get into a lot more at the end of the chapter to do some fun proofs with it and some problems. But for now, the absolute value of a set x, so where x is a set, is the cardinality, which is just the size of x, so the number of elements. So some people use cardinality in a different fashion. I've seen it used as just to mean the number of elements, but in our cases, this is what we're going to use in this section. Our absolute value is the number of elements. So our function, f of x that equals the absolute value of x, is saying take that x that's a subset of the power set of A, B, and C and map it to its size. So if we're going to construct an arrow diagram, we need to know what the power set of A, B, and C is. So our power set consists of the empty set. We have just the singleton sets, A, B, and C. We have the double sets, A, B, A, C, B, C. And then we have the improper subset, A, B, and C. So we're going to use this particular example to really discuss codomain and image. Well, they're the same thing. But for now, let's just go ahead and map this. So f of x, the size here, there's nothing, it's the empty set. So this is 0. The size is 1 here, the size is 1 here, the size is 1 here. For all three of these, our size is 2. And here our size is 3. So our function, capital F, maps that power set of A, B, and C, we said, into the positive integers. And Z plus is the codomain of capital F. Now, I've been saying that the image and the codomain are essentially the same thing, but that's not necessarily the case. So the image of our power set, P of ABC, the image is the actual values that we get to in the codomain. So the image is always a subset of the codomain of F. Now notice that the image, you can think of it as a set on the domain. The codomain and the domain are sets on the function. So this set, which is just the set 0, 1, 2, 3, is a subset of our positive integers. So in the next section, we're going to be talking about when do these two things actually equal each other and what does that mean. It gives us a very particular property. But for now, you can take heart in knowing that the image and codomain are related by this property here. So if f maps x to y is a function, then y equals the codomain of f, and the image of x, sometimes we just denote this as img of x, equals the set of little y in capital Y such that f of x equals that y, where x comes from x, the set x. So our image on the domain is specifically the elements we map to. And the image, img of x, is always a subset of our codomain y. Now you can take images of subsets, and we'll define that in a second here. But what we're doing is we're saying we can look at our domain and we can take a snapshot of that domain. The codomain could be bigger. A lot of times we're used to the codomain not being bigger. But the codomain is what, as I said at the start, is what we know as the range from previous courses. Now we're calling it the codomain because a lot of times we teach range as it's the things that you map to. Well, the things that we map to are actually the image of our domain, and the codomain is the set that our image lives in. So if we want to take an image of a smaller set, so if we let A be a subset of X, then we can take the image of A, and this, just like the image of X, is the set of Y in our codomain such that Y equals f of X, where X now lives in A. So that's our image of A. So you can always take the image of the full domain or of subsets of the domain. And you can also do the reverse. So we can take the inverse, and this would be of y. So the inverse of y, that takes x, which are in capital X, such that f of x is an element of y. That's the idea of inverse, and we call this the inverse image. So this is the inverse image of y. Notice how it's defined here. The inverse image of our codomain is simply the x that we have defined by our function. So even though we've distinguished between codomain and images now, the inverse image only looks at the elements that would get us back to y. So I'm going to say that again here. Our inverse image only gets the elements in our domain that would actually be in our, that would actually map to elements that are in our codomain. So there are other elements, or potentially other elements, because we know the image of x is a subset of y. So there could be other elements of y, but we ignore those by this definition, because we're only looking at elements that when we apply the function f, this should be capital F, we get back into our codomain. And we can do the same thing that we did. So if we let C equal the image of A, the same A here, then we can form the inverse image of C, and this is the set of x in X such that f of x is in C. So this looks at just the elements that got from A to C, and it takes only those elements x. Now notice we're not writing A here because they don't need to be in A. If they're in X and f of x is in C, by definition, C is the image of A, so that means these are the elements that equal f of x that came from A. So you could technically write A here, but it's more proper to just write x, because with this requirement and this definition of C, we will never not have an x, a little x, that's not coming from A. It's just not possible. And this would be the inverse image of C. So this is the inverse image of C. So there's some homework problems that take you through these and work with these images, codomains, functions to get you kind of used to how these sets work. And it's a little bit different because unless you've seen image and codomain before, probably not used to it, and it just takes time. But you know, if you need some help, come see me in office hours and we'll get through it. But we have one last little thing to talk about in this section, and then we'll be done with 7.2. So that is well-defined functions. So a function, in quotes, is not well-defined if it fails one of the requirements being a function. Now you might be saying, well, if it fails one of the requirements, is it a function? And the answer is no. That's why I have function in quotes here. As it turns out, it's a lot easier to think about things that are not well-defined than functions that are well-defined. So remember, our requirements are that if we have this function, quote-unquote, x into y, that for all x in x, f of x equals a little y that's in y, and for all x in x, f of x does not equal y, and let's call this y1, f of x does not equal y2. So I'm using some shorthand here, but these are, I keep doing little f, break myself of that habit. For every element in our domain, it's related to something by f in y. And for every element in our domain, it is not related to two things. It's related to one only. So if you fail either of these, you are not well-defined. You're not a well-defined function. Now the reason we say function still is because maybe you change your codomain and you change your domain and you have a well-defined function. But we've seen non-well-defined functions for a long time, and we treat them like functions. So the classic example of something that's not a well-defined function is the circle. So if you think about x squared plus y squared, we'll just use the unit circle. And if this maps x into y, and we'll say that f maps reals into reals, and this is our relation equation that defines our function. Well, we know that this isn't well defined because we know that if x equals 2, for example, so then we would have 4 plus y squared equals 1. There's no choice, or there does not exist a y, such that y squared equals -3, because that's what we would need. This would be in R. So if we change our codomain, though, if we change this to complex numbers, well then we would need y squared to equal -3, so y would equal I times the square root of 3. Well, now we have an element that works in our codomain. So now, if we redefine a new function, we'll call it g, and this maps reals to complex numbers, and this is x to y, by x squared plus y squared equals 1. This g is a well-defined function. You can always find a proper x and a proper y that makes this true because you allow for complex numbers. But when you only allow for real numbers, we know that we have an issue. So this is the idea of why we call them well-defined, not well-defined. It's why we say a function is not well-defined, and it's because there's an issue with its codomain. If you change its codomain, you can get a well-defined function. Maybe you have to change its domain too, or one or the other or both. But that's the idea behind well-defined functions, is you need to satisfy both of these properties. Related to every element in x needs to be related to an element of y, and you can't be related to more than one. This is not a function. But you could be a function if you change your codomain or if you change your domain or both. So that is the end of 7.1.